Hi everyone. I'm
Shivam.
and we are presenting on like the talk is titled like streaming aggregations at scale using Kafka and Kafka Streams. So this is a work that both of us did when we were in platform team earlier in Sharechat. So the little bit about like what it is and what Sharechat does. So Sharechat is basically a social media company, and as a social media company, we maintain a lot of counters, like everything from views, likes, shares, and the list goes on. Honestly, it's a lot. And operating at the scale of Sharechat, where we can probably have like sometimes like 100K counter updates per second, especially on counters like views. We saw some problems where our key value stores, where we are storing these counters, were unable to scale up. There were like severe hotspotting issues, and this we wanted to like build a solution which would take care of like all of these things and also probably scale up to like even 10x the scale that we were at when we started with this, like something like 1 million like updates per second. So this talk is about that. But before that, I will have a little bit of backstory, and I'll explain like why counters are difficult. So this is a very old post from Wired, where this is about like this is a very famous thing that happened in Instagram started off. So Instagram had a very big celebrity problem. Like whenever Justin Bieber posted anything, the app usually went down for a bit, and that was because like Justin Bieber was on everyone's feed and everyone tried to like that post, and that caused an issue in the database because of which no one was able to fetch the like count of of like his post. So it's a very simple thing. So basically think of it like this. So you have a lot of users, and then let's say like a user Beatrice and a user Bob is liking his post, and but then for Justin Bieber there will be like something like a 1 million users liking his post. It would be impossible to calculate if you do a select star. Even if you cache it, there will be times where you go to the database, and that will be very hard to do. So the simplest solution to this is to denormalize, basically, right? Like you don't need to have so many rows that you have to scan over. So you can have like a denormalized counters table, and what you can do is you can store like the counter for let's say Justin Bieber here, and then the like count, view count, etc. Now this is probably problem solved, but then do you see the problem here that can happen? The main problem is that there can be too many updates, which can lead to like hotspotting issues. It's a famous thing. It's called a celebrity problem. Actually, that's why it's called a celebrity problem. And so back to ShareChat, we had something of an issue which is similar to this. And so what we did was, so the reason was we are using Bigtable back then. So Bigtable has a concept of something called a hot tablet. So Bigtable has a concept of tablets. A hot tablet is basically one tablet which is overloaded. Basically, it is receiving a lot more, I would say, requests, and it is unable to scale up, which will lead to like a very bad latencies. So the problem with a hot tablet is that no matter how many times you attempt to scale up the database, there will be one like tablet which will be very hot, and you cannot like shard beyond the extent, because for that user you would anyways, and it will anyways go to the same core or the same tablet that will define it. So what you need is something of a better work distribution. So the first thing that anyone thinks about this thing is a distributed system. The first thing about distributed system is like add more servers. So let us try with a solution. Like we add more servers before the database. So this is where we get to, and we have let's say 3 servers. But do you see a problem here? Like let's say there are the different likes coming. Like green is separate, orange is separate, blue is separate. So the server aggregates and sends it to a database. Now the problem, like, can anyone figure out what's the problem here, like in this kind of system? Yeah, you would have to take a lock because there are multiple servers updating like a single value. So basically race conditions, right? So the race condition. The second thing is like, even if you look at it, like let's say the blue is coming both to server 2 and server 3. It's not like an optimal distribution. You'd probably want to reach somewhere which is much better. So I would not explain much more on this because there's a very good video by one of my favorite YouTube creators, Tom Scott, and where he explains about why computers sometimes cannot count. You can look at it later on. But like we want something like this, which looks much more better. But this is an ideal state. Like how do you get to it? Because there are no race conditions here. The single server is processing everything, so you don't need to take distributed locks. And there was a very like optimal distribution of work. So we can start off probably with something like put all the events in a Kafka topic and then partition by the key which you are like aggregating on, and then have servers reading from this. So this looks much better, honestly, if you look at from now. And it is achieving like whatever we wanted to achieve. But even this, I would say, has a few problems. Now, what problem can you see here? I think anyone can tell me the problem with this system? Sorry? Post ID is fine actually because post ID has a very big distribution. It is not like it will get hotspotted any time. Like it is pretty evenly distributed, honestly. But yeah, I get what you're trying to say, but I will come back to it later. Like that is not a problem. That is still fine because even if the post ID key space is pretty huge, the key space for the partitions can be small. Like that does not matter. The actually one big issue is what if one server goes down? So the updates for that thing is missed, right? Because you will probably want to keep those updates for a while and then serve it to the database because you want to batch. You don't want to like store like you don't want to send every update like instantaneously. Because that is what we are doing, right? We were trying to batch those updates and have a single update go to database. That is how you reduce the load, the write load. So, so how do you solve this? So one thing that you can do is why not just add a database everywhere, like for each of the pods. But this is easier said than done, honestly. So enter Kafka Streams here. So Kafka Streams is basically an application framework, but it has, so internally it's a stream processing framework that has support for stateful streaming. So basically it can do stateful aggregations. And internally it uses RocksDB, which is our state store. And if you use Kafka Streams, you can have like all those, you can implement a batching, which is stateful and it is correct. Where like even if the server goes down, you would probably not lose lose data. Like you can have it like operating in exactly once or at least once. Both of them have their own trade-offs, and that is what we tried. So again, like if you have this thing with Kafka Streams, there will be no race conditions, optimal distribution of work, and then the third point that we added is a durable aggregations. Like aggregations would not go away even if the pod goes down. So I had written a much bigger blog post on this, which has all of these details. But I will not explain that in so much detail. So Shivam would be presenting on like the system that we build and what we have done there. Yeah, over to you, Shivam.
Hey guys, so I think Shom explained the problem well, right? Again, there's like hotspotting. We build the system using Kafka streams. How does the system look like? Okay, so this is basically the pretty much the architecture of platform counters framework that we built, right? As you can see, like if we go into the components here, right? These are the different components. We have some ingest topics where product teams are actually pushing their counter events, right, directly into the system. We have Kafka stream apps that are running, consuming from these ingest topics, right? Again, we have something called counters, metadata service, and some components called triggers, right? We'll actually go into details in the later slides, right? One important thing to note here is, right, we had a per table, per topic kind of configuration. It's like a multi-tenancy thing. So for counters that were stored in a single table, we just had a single Kafka stream setup, right? So yeah, so let's go into the details of every component, right? Before that, at in-house Kafka setup, we initially started with 9 brokers. I think each broker had like 16 GB RAM, 16 cores, 64 GB RAM, and it's like 1 TB SDD. So again, we were vastly overprovisioned because we wanted to do everything right the first time, right? And if something breaks, then we can basically, if something works out, right, we can just simply scale down later on. Okay, so Kafka streams, how did we actually achieve these aggregations? So these are literally the 3 lines that were required, right? So we are grouping by key. So initially in the system, we had like a very fixed schema for the keys for the events that are coming to us. We had counter name and the entity for which basically the counter need to be updated. So the first line actually does exactly that. We are actually building a stream where we will group them by the key that is present in the event. The second line actually builds this aggregation window, right? So in the system, we actually had multiple aggregation windows. So people can basically say, okay, I want to update in, let's say in 1 second, 10 second, and so on, right? So the second line actually achieves that. Third line is exactly, so third line is so in Kafka streams, whenever a new event is added to a window stream, right, a new event is actually generated. All these events are not required by us because we only want the event once basically all the value is aggregated. So this is basically suppression of those extra events that were actually coming to us. So that's it. 3 lines of code to actually get the aggregation support in Kafka streams, right? Okay, again, as I said, right, we had same key partitions. This actually ensured that for an entity ID, or it can be a post or a user ID, right? For a single counter, everything was going in a single partition, which means same Kafka stream task or app will actually process this event. And so there is no actually concurrency issues or anything that is like the data is not updated, right? We are using RocksDB as actually Shom explained, right, for persistence of local state, and we were actually backing that by Kafka changelog topics, right? These topics basically, let's say your Kafka stream app went down for whatever reason, right? How would you actually store the state, right? So that's where the changelog topics come in. We can actually replay all the events in the topic, and all the state that was there in the Kafka app will be actually rebuilt. the optimizations. As I said, right, we had actually multiple aggregation intervals. Another reason was, right, was that, like, let's say you have made a post on some social media, and you are actually like tracking all the likes that you're getting on the post, right? Let's say for the first 100 likes, right, everything that you want might be real time, right? Basically every increment is like a validation to you, like, okay, you feel good. But after, let's say, 100 likes or 10,000 likes, right, you don't really care if it is increasing by 1 or 10 and so on, right? Or if it is increasing in real time or after some durations. That's why we had like I think we have like these four different aggregation intervals, like real time, 1 second, 60 seconds, and 5 minutes. Okay. Oh, the second component, right? It's like counters metadata service. Now we have lots of counters in the in the organization, right? And each counter has their own aggregation intervals. Then again, we have something called triggers that I'll go on later on. All this data need to be stored somewhere, and we do not want to store it in the Kafka Streams app, right? So this is basically a simple CRUD-based service which stored all this information. What are the counters that are present in the system? What's the aggregation interval, triggers, and so on. We are using some caching because, again, once a counter was created, right, and the information was stored in the DB, it did not get updated that much, right? Once you are sure, right, you want this aggregation for this counter for this range, you don't want to change it like too much. So again, caching work kind of like a very simple service. Okay, triggers. Now again, I've been talking about triggers for a lot of time, right? Again, what these are. So think of this example of a notification, right? For your post, whenever your like count goes above 100, right, you get a notification. Okay, here your post has actually received more than 100 likes. So congratulations, you have made it. Like you're famous now. Something like that. Any time a counter actually crossed a certain threshold, we generated an event. Later on, the product teams actually were using these events for later processing. They might be using it for, let's say, sending some notifications. We also had some gamification in the platforms. So again, your awards will unlock for certain I would say milestones, right? Yeah, that's the major use case. I think there was one more where we wanted to actually moderate the post, which has received certain number of views. So something like this again. And this was one of the biggest lever that actually achieved, that actually helped us drive the adoption of this framework in Sharechat. Okay, so again, we have understood triggers, right? But internally, for storing these triggers, we were actually using different topics for even a single counter. For a single counter, if let's say if you have 100 triggers, right? They might be stored in 10 different topics. So again, we wanted to provide the product teams just single topic where they will get all the trigger events for their event, right? So this is where we wanted to build basically a glue jobs which can basically fan in all these events from all these different topics, let's say 10 here in my example, right, to a single topic. That's where basically Benthos came in. It's called Red Panda now because actually they acquired it and renamed it. But yeah, it's basically the same thing. It's a declarative data streaming framework. It's like if you want to build something stateless and dumb ETL pipelines, it's very convenient. It provides you at least once guarantees. It's completely stateless, right? Again, there is inbuilt support for logging, tracing, and metrics. It's actually written in Golang. It's like a small caveat. Okay, you can't see it very much well, right? Basically, this is the code that we had initially before actually we introduced Benthos in the system. Right? This is the Java code for actually consuming these triggers from these different topics and sending them to a single topic, right? And this is the Benthos code. Now here, this is just a single function that is a consumer, right? I have not actually included here the different files, resources for logging, right? For metrics, client creation, and basically producers and consumers, right? So this is just a single function in the Java applications. In Benthos, this is the whole job for basically consuming from, let's say, 10 topics or 5 topics, processing them, and then sending them to a single topic like later on, right? So we'll just break down the Benthos configs a bit more to get an idea of what actually was being done, right? So you see, right, this is the input. Here we just basically say, okay, this is the Kafka broker, and these are the topics that you have to consume, and any extra configs that you want to add, right? Start from old days, target version, and so on. This is actually the processing. Once you have actually received the event, what do you want to do? So basically here we are actually, it's like very simple, right? We are actually decoding the event from protobuf. We are actually storing all the events internally in protobuf format. So we are decoding them, and we are building a new payload that will be sent to the product teams, right? For their use case. Output. Again, as simple as that. I want to send this event to a GCP PubSub topic in Marchprod project, and this is the topic name. That's it. It will actually send everything there. No other basically setup required from our side. And again, as I said, inbuilt support for logging and metrics with just these 5-6 lines of code, right? Again, I'll just simply say, tell you how the performance was for Benthos, right? Again, this is a small message that Shom sent once he actually set it up Benthos, right? So we were actually processing 3 Mbps of messages, right? Throughput, basically 2,000 messages using just 1 vCPU, 1 GB RAM at 90% CPU utilization. It's very, very cheap, right? I think if we have dozens of jobs in the Sharechat, right? And they have less than 300 rupees per month cost for actually consuming all the dumb jobs that we have in Sharechat, right? Again, Now, maintaining all these YAML files for defining these jobs, it's hard, right? So what we did is we platformized Benthos also. It's a small cookie cutter mono repo, right? You can actually have your jobs in simple folders. There is a common basically build script and common CI and CD that we provided in this basically mono repo, right? This is a generic dashboard. So as I said, right, Benthos actually exposes lots of metrics. We just build a one generic dashboard for all the Benthos jobs that are present in the organization. Now teams can actually use these dashboards to fine tune their applications or to put any alerts if they wanted, right? Yeah, frankly, this is not enough to talk about Benthos. So we have a separate talk that you guys can check out, right? Basically, Benthos, what, why, and how. Okay, so back to the basically Kafka setup or the framework setup, right? This is basically the dashboards. If you have so basically we are using in-house Kafka setup, right? Now this Kafka setup as well as Kafka streams now maintaining this is hard if you do not have observability. So this is an example of the dashboards that we had in the organization. These are not obviously all the dashboards, but this is like the first 4 dashboards that I could find in the system as of now. Observability, what we were using to actually build these dashboards. There is a blog by Datadog, which is like very good blog. It is still one of the best blog for Kafka metrics, right? We had tools like CMake and cruise control for managing the clusters and K-minion and Kafka like exporter for actually building these observability dashboards. Okay, so this is basically the number of counters that we, once we actually built the whole system, right? We started with like 2 counters that were onboarded to the framework. And by the end of the year, right, we had like more than 16 counters that were there in the like basically whole framework. Okay, I think we have built the system, right? Now we want to talk about the optimizations like that were required to actually scale this framework to the scale at which Sharechat operated at. Over to Shubham.
Thanks, Shivam. So I am struggling a bit with this, but then I think I got it correct. Let's see again. Yeah, I think this is the best I can get. So optimizations, yes. So the thing about any like state processing system, especially one that has a lot of state, is that managing state is hard. Like managing state is always hard. So we so the thing that I think I'll just remove it. So thing that comes with state is that there are like the biggest thing that was affecting the state was rebalancing. So rebalancing is basically something that happens in every consumer group. So when you have a stateful consumer group, it is further affected by these rebalances because when a rebalance happens, it can have there are large delays in message consumption, and there's a state movement that happens from each pod. So that can lead to huge delays. And we actually saw this in production. So this is a production graph that we have, and you can see that we had like around, especially at the peak times, that is at night, we had a huge lag, like 40 million or 60 million lag. And we thought, let us try to solve it. So you cannot actually solve what you cannot measure. So the first thing that we did was we picked like one metric, which is a North Star metric, which is a lag. So we would try to optimize on the lag and then see what would lead to this like L0 metric being optimized. So before we start with this, there's like one thing that you need to probably learn about Kafka rebalancing, consumer rebalancing, is that it's very complex, but there are like a lot of good resources that you can read about. So back when I started, this was probably the most famous resource. Like this is by Gwen Shapira, who was then a part of Confluent, and there's this talk by her on the Kafka rebalance protocol. And right now, if I were to sue, I would probably read some more Responsive's blogs. Responsive has very good blogs, honestly, and their blog on rebalancing and how it happens in Kafka streams and Kafka is really good. And okay, anyways, freaking a photo, I'll just keep it. Yeah. So there's a lot of depth actually that one can go into for rebalancing. But overall, I would say we would want to optimize for some simple metrics or indicators. So one of them, very simple thing, how to reduce rebalancing. Number 1, reduce number of rebalances. Number 2, reduce the time for each rebalance. Again, break the North Star metric into 2 North Star metrics. So we try to do both. So first thing would be why was state restore slow? So the thing is any stateful application. So as I said about Kafka streams is a local RocksDB instance. Now the local RocksDB instance was we were using a deployment. So the local RocksDB instance was actually in scratch storage. So anytime the pod restarted, that state would actually go. But then because it was part of the Kafka streams, so what it will do is whenever it came up, it will again try to load the data from the changelog topics, because every change is actually durable within the changelog topic. And that is how it maintains durability. So the changelog topic, actually we saw that got very large. In fact, it could grow to terabytes in size. And we tried a lot of things that did not work. So one thing that we did was like I actually did manually, like I logged into the Kafka, back then it was in-house Kafka, so I logged into the Kafka cluster, saw like all the files, and I realized that compaction was actually not working properly. So one change that we did was like change the segment.ms to 4 hours and add a jitter of 1 hour. By the way, jitter is very important if you're adding segment.ms, because whenever the segments roll over, they roll over all of the segments roll over at one go. So that one create a thundering herd. So like if you're doing segment.ms, be sure to add segment jitter.ms, because the default config is on is not on like this timestamp. It is on usually on the size of the partition. So size, different partitions reach at different times. So that automatically gives you some sort of a jitter. But if you're doing by segment, you will have a jitter. So one important thing that we had was that now this is what will help us the compaction. But still we realized we can go further, we can go even more aggressive, because none of our use cases had an aggregation that was like greater than 1 hour. So what if we did things that are pretty dangerous, which I would not recommend a lot of people to do. But I changed the internal topics from like cleanup policy from compact, delete. So because I do not want to wait for it to like compact and remove the things. It is better like even if you delete, because I don't care like about beyond an hour. So I just changed the retention manually to 12 hours, and then I updated even further. Here it is in 12 hours. And the core takeaway from here should be like Kafka actually keeps data much longer than you think it does, and that is mostly due to how compaction and retention works. There are a lot of like good the defaults are pretty high. There are a lot of good blogs on this that you can read. Like I really like a one by Strimzy. They had a very good blog post on both of these. And the result was that our state reduced a lot, because it was reduced almost by 100x, and we could like restore from like 20 minutes, it took to less than 1 minute to restore the state, which helped a lot for us. But then like we come to the second problem, like okay, so now state restore is fast, so even if we have rebalances, we will not be affected as much. But what if we can just reduce the number of rebalances? That is probably another important thing that we should look at. So like there are three main causes when a rebalance can occur, like basically. So when a new consumer joins in, because you would want to assign some tasks to that consumer, that is like a join group request that happens. Or when the consumer disappears, because okay, so that consumer is gone, so you want to assign its task to someone else. Or there are two other things, like the consumer can probably be too slow, basically. So that is like usually this is used to check for like very slow consumers or like deadlock like check. So all of these have their own mechanisms. So there's a heart beating which checks for consumer disappearing, and then you have like a max pole interval MS that actually checks for like consumer is active but is not able to process events. So a few observations that we had was we're missing a lot of our heartbeats, like, and the session timeout, we are missing a lot of our heartbeats, resulting in the consumer going out of the group and then triggering a rebalance. So we did a lot of analysis, and we realized that there were some out of memory errors and some GC pressure, and that aligned very well with those rebalances. So we like hypothesize is mostly caused by GC stalls. Again, like it is very difficult to analyze exact one-to-one correlation, but we use like good tools like JFR to check like what is happening. But the solution was very simple. We just upgraded our Java version and things worked fine, because like that's the core takeaway. Like you can do a lot of complex things, but the simplest things sometimes work the best. So always keep the Java version to be the latest. That helps a lot, especially with GC. And I think furthermore than that, like because we are optimized it beforehand, also we reduce the number of pods, like the number of consumer pods. So we are now scaling much more vertically. Like each pod had like, instead of going like 1 core, we had like 2 core per pod, and we had much lesser pod. And like the consumer group rebalance protocol actually is it has a bottleneck on the number of pods. Like it will not a bottleneck, it will scale to a lot of consumers, but it will probably be harder, because any consensus protocol would have a difficult time maintaining consensus between 500 people than between 10 people, right? So obviously, if you have less number of pods, it always helps. So yeah, so this is the result. Again, all of these are production metrics. Our rebalances went up like, so we can look at this one metric, the last rebalance seconds ago. That's around some 5 days. So earlier this never went over like 4 to 5 hours. Now it was like in days. And so we had like, so this is like a dashboard that I built that has like all the important metrics that are grouped. So for rebalance, we had like these 3-4 metrics that are like L0 metrics. And once we had this done, like that was it. So this is like the graph. You can see like earlier we had like 20 million, 30 million lag. And now we have like 20, 30K at peak, which is again the same exact throughput, which is like very good change. And apart from that, we did also a few more improvements. We improved the end-to-end latency for our framework. Like it was something around like 30 seconds to 1 minute. Plus the aggregation interval, we upgraded to something like 1 to 2 seconds. And that was mostly due to like one mistake that we did initially when we built it. So we had a repartitioning step. So in Kafka streams, or in if you have heard of anyone like aware of like what is a repartitioning in Kafka streams, or like in Flink, you heard of a shuffle in Flink, or probably in Spark World, heard of a shuffle. So cool, I'll probably explain it in a bit. So a repartitioning is something that happens when in Kafka streams, whenever like what happens, you have a change of key because you aggregate on the key. So let's say you are aggregating on user ID. So let's say every pod gets a certain user ID, but then you want to aggregate, let's say, on something like a post ID, which is like something else. So you have to again reshard the things because that is how you will aggregate on the post ID. So this happens to something called repartitioning, where an internal Kafka topic is again involved, where you repartition and then change it the key internally. So all this happens internally in the streams framework, but we saw that was happening. We visualized our like streams topology and saw this was happening. So we entirely removed the repartitioning step because it was like not that useful to us and not required. So we removed it, and that is how we got it down. And in fact, even if you have your Flink jobs or your Spark jobs, like look at your shuffles. Shuffles can be really expensive, especially in the networking and CLI and deceleration part. So it's always beneficial to reduce shuffles. And so we come back to the like all of this contributed a lot to like a cost. This is our actual cost graph that we had from January to June. And we had some like 90% cost savings from all of these things. And this was only possible due to improved stability of our system. Because as Shivam also said, like we are incredibly over provisioned at the start. And you have to be, because if you when you're launching something, you're not sure if it will work or not. So you want to probably solve for the business first. And then now when we are like so confident of our system that we know all the things in and out, then we can probably scale to right size the system or probably optimize it further to the scale where it will be working. So now we come to the final part. Now everything is tested, everything is working well. So what if I just increase the scale to 10x? And then we didn't even like do a load test. What we did was we did a very realistic thing where we just we had a parallel Kafka setup and we stopped our consumers for a long while. And then we said that, okay, duplicate the Datadog parallel Kafka setup. And then you start from there. But this time you have a lot of backlog accumulated. So that helped them like to scale the consumer to very high scale, because we would never get production traffic at such a high scale, but it helped a lot to see like what would happen if the production traffic changed like 5x or 10x. So this is actually a graph from where we're processing like 500k records per second, and we did not see like any lag or anything. And we can even increase to like 1 million records, and that would still be fine. Just we need more pods, because each pod at this moment was processing around 2k records per second. So again, like, okay, we optimized it, and I give you a few strategies, like, but how do you optimize your Kafka Streams application? So before, like, when we wrote this framework, like, there were a lot of blogs like scattered everywhere. But right now, I would recommend like there's this 2 blogs by Responsive, like, which are very good, like these 2 blogs. And I would recommend like everyone who's like using Kafka Stream production to go through this. They have a lot of those configs, which for us were very important, but they have distilled it to like what are the important ones. And so yes, concluding remarks. So in the end, like, project was a success. You can see from the metrics that we see, and the DB latency was much better. And in fact, there's another thing that we did not list here, because now before every counter update, you have like this Kafka Stream setup that actually helped a lot in our migrations as well, because now we are not coupled to a database. Like, not the update directly does not go to database. So when we are migrating our database, we migrated it once from Bigtable to Scylla, or sometimes from Spanner to Scylla. So we were helped a lot by this system, because this system could absorb and act as a buffer where you can keep and directly change the database without like caring about other things. So that was very helpful for us. And that was all. And this is a graph that I had for our input versus output. So if you can see that the input changes a lot, like at peak it can go to like 100k messages per second, but the output stays more or less consistent. This is because of aggregations. Because it does not matter how many events you have. What matters is the number of unique keys, because after you're aggregating them based on the keys. So that's all that I think, yeah, that's all that I had. And any questions?
Can you go back and explain that first 0 to 1 count versus 1 to 100, 100 to 1000 count? What was that logic behind and how it was handled?
So this is basically like saying for any counter, right? As long as the value is basically within the range of 0 to 100, we will do all the counter updates real time. So for every event, we will actually do a DV update directly, right? But once we actually move on from 100 to, let's say, 101 to 1000, right? We can now aggregate these counters for 1 second before actually making an update to DV. So this is basically as your counters scale up, right? For a, let's take the example of the same one that I took, right? Like count. If your post has 100 likes, right? Now if they're increasing, let's say at every 1 second you're actually getting the updates, it's fine for you, right? If it increases again from 1,000 to, let's say you are getting to 10,000, now you can still take more and more time. This actually reduces the load on the DB, right? So for a post that is actually more and more popular, your DB doesn't still get overwhelmed because you are actually aggregating for a higher interval.
So basically, once you receive the request, you check in the DB for the current counter. If it is less than 100,
No. So can you go back? Just one.
I can probably explain that as well. So what is happening is basically that, think of it this way, that we don't actually need like an actual count. So whenever you think you're on Instagram and you are sending a like, you see some approximate number, right? So 23 million likes or 23 likes on that number. So we actually use that number that is sent by the front end. So we don't like take a get call from the database. We actually see the front end number because we just need an approximate interval to put it into. Let's say if you have like 1 million likes, we'll put it into the last aggregation interval. If you have like a 50 likes, it might not be accurate, but we'll set your aggregation interval accordingly. So internally, this is basically a topology. The Kafka Streams topology has like multiple like intervals that it aggregates on, and you basically have a step where you can send like what topology you want to send it to. So we like what part of the topology you want to send it to. So we send it based on this count.
Hi, I have a small query on again the same interval logic. So you are using this aggregation and all, right? How do you manage the retention for that K tables that you are creating in the RocksDB? And did you face any time zone issues from UST to EST or EDT or any other time zones or any other countries, because Sharechat is used across time zones? Like, how do you manage the time zones? Any issues? Because the K table, if you use retentions and all, every timestamp that is managed is in UTC, right? How did you solve that?
So, like honestly, Sharechat is mostly in India, so we don't have that problem a lot. But I would say that so there's a concept of time in stream processing. We use you can use something called a wall clock time or event time. Here in this use case, because we don't care like when the aggregations go, like it's like you have to at the end you have to reach the database. We use wall clock time. So in wall clock time, actually your things are very simplified because you don't care about late events or you don't care that much about like your exact time semantics. So it was not that an issue. We just wanted that we would because we are protecting more than like having like the like it does not matter when exactly the like goes in. Like at the end, it should go into the database and increment it.
Not only like likes, you didn't have any of your counters that had to be reset at midnight, or any of your counters that had to be reset for any person or any profile. None of the counters had to be reset for anything.
Rechecked. So you mean that
reset? The counter has to go to reset and then 0 and then count back again. You never had any of your counters like that. So if you had to reset, then the Kafka table would automatically get reset.
But
right?
yeah, but why would the counters like reset? Because
No, I'm just asking if you had any use case.
No, because I think in the database like they're not, honestly there are not that many people in India to like exceed like, I think 4 by 10 is anyways 2 billion, right? So you would probably not reach that number with any of the counters. But in databases, I think even if you like use a int type, it has like internally databases have a representation where like basically in Scylla we have something like counter type. So internally it will not reset, like it will be keep on increasing. Like
only in the RocksDB. Only in the RocksDB it had to. You'd have to reset your RocksDB, right, so that it gets cleared. The changelog topics gets cleared somewhere. Otherwise, the changelog topic will be there for eternal, right? You'd have to have retention settings for your K table. Otherwise, it will be there, right?
Sorry, I did not get you. I think, but we did not have this issue that you're speaking about. Maybe we can discuss later on this. Thank you.
Thank you.